All right, we're going to do some examples here. Determine if the following functions are polynomials. If yes, then determine the degree and leading coefficient. So the polynomials in this list are of the form where you have real numbers multiplied by terms that have x, powers of x. So we see that here, and they're strung together. We see that here, and the other examples here are not polynomials because here we have an x in the denominator. That's a rational function. You have a polynomial in the numerator and a polynomial in the denominator. Here we have an x under the radical, and here we have x to the power of 1/2. Polynomials have integer powers that are positive integers or 0. The constant term has an x to the power of 0, and then all the other ones here, x to the 1, x to the 2, so on and so forth. They're positive integers. So these two are polynomials. And here we have degree 5 because it's the highest power on x. And then the coefficient in front of that is just understood to be 1. So the leading coefficient is 1. And here, the highest power on x is 4, and the leading coefficient is 3. So we have degree 4, leading coefficient 3. Okay, now in the next problem, we are asked to circle the following functions which are quadratic. So this is an absolute value function. Here we have a square root function. Here we have cubic, and here's quartic. This is the only quadratic right here. Quadratic functions are parabolas, and they're in the form of f of x equals ax squared plus bx plus c. So this is the form of a quadratic function. And here we're missing the middle term. B is 0, but that still is a quadratic function. Here we have a square on the y. It's got to be f of x. If you replace that with y, there's not going to be a square. So this is not quadratic. Here we have a radical, and we have a quadratic function under the radical, but the result is not quadratic. Here we have a quadratic function. You can see degree 2, leading coefficient -1, missing the middle term, but that's still quadratic. And here we have absolute values around a quadratic function, so it's no longer quadratic if you put those absolute values. This is actually quadratic. Even though we have a square root, it's just the 2 that is under the square root. So this is just a real number. Square root of 2 is approximately 1.4. So we're missing a constant term, but this is still in the form ax squared plus bx plus c, where c is 0, and b is square root of 2, and a in this case is -3. So this is quadratic. All right. Use the given information about the polynomial f of x to write its complete factored form. So we are told that it has zeros 3 and -3/2, which means that x minus 3 is a factor and x plus 3/2 is a factor. And then the leading coefficient is 2. So this is the factored form. Here we are told that it has a leading coefficient of -3. And 0 is a 0 of multiplicity 2, so x squared is a factor. 5 is a 0 of multiplicity 3, so we have x minus 5 cubed. The powers on your factors are the multiplicities. And then -2 is a 0 of multiplicity 1, so we're going to have x plus 2. So this is the factored form of our polynomial, given that information. All right, in the next problem, we are going to find the vertex for each of the following quadratic functions. So here, the vertex is just the absolute maximum, and that occurs at -4, 2. So the vertex is -4, 2. I don't know if you probably can't see that on the video, but when you print out the paper, here, this is a 4 for X, and this is at a height of 1. So this is 4, 1. And that parabola has a minimum value of 1 at 4. And here we have a maximum value of 2 at -4. Just some extra information there. Now this is in the form, this function is in the form f of x equals a times x minus h squared plus k. So to identify the vertex, this is the vertex form of the quadratic. We look at this constant, so h is 3, and that's the first coordinate of your vertex, and k is square root of 2. So our vertex is 3 square root of 2. Here, we also have it in vertex form. It looks like k is 0, and this pi, we're subtracting h, so this is plus pi. So pi, or negative pi, is the first coordinate, and 0 would be the y coordinate. Now here, it's not in vertex form, so we have to use the vertex formula, which is x equals minus b over 2a. So here the vertex is going to be minus 3, which is our b, over 2 times a, which is -1. So that's going to be 3/2. I'm kind of running out of room here, so let's go up here. All right, so the first coordinate, the x coordinate, is 3/2. Then to find the y coordinate, we have to plug 3/2 into our function. So y equals minus 3/2 squared. I'm just plugging 3/2 in for x, plus 3 times 3/2 minus 7. And this is going to be minus 9/4 plus 9/2 minus 7 is 28/4. And so this is going to be 9/4 minus 28/4, which is going to equal -19/4. And so our vertex is going to be 3/2. And -19/4 is -4 3/4. So that is the vertex. All right. Circle the following functions which are rational. So you have to have a polynomial in the numerator and a polynomial in the denominator. So this numerator is not a polynomial because of that power is negative. The power on x is negative. So that's out. Here we have a quadratic function, which is a polynomial, and here we have a linear function, which is a polynomial. So this is a rational. Here we have a constant function, which is a polynomial, and here we have a linear function. They're both polynomials, so that's rational. Here again, constant function over x, which is a linear function. These are both polynomials. Now here we have a square root of x. X is under the radical, so that's not a rational function, because square root of x is not a polynomial. Here we're asked to find the domain of the following rational functions. So you just set the denominator equal to 0 to find out which values of x do not work. So if you factor this, x minus 5 times x plus 3, set it equal to 0, we see that x cannot equal 5 and x cannot equal -3, and that's because you can't divide by 0. So there's no zeros in the denominator. So the domain is all real numbers, all reals except 5 and -3. Here, 5/3, x cannot equal 5/3. That'll make the denominator 0. So here it's all reals except 5/3. The denominator cannot equal 0 here, and that's because 3 times x squared is a positive number plus, and then you're adding 5, so it will never be 0. So the domain is all reals, all real numbers. And here, it's already factored for you. So t is not equal to -1, it's not equal to 7, and it's not equal to -3. So it's all reals, all real numbers, except -1, 7, and -3. Now to find the vertical asymptotes, you're going to set the denominator equal to 0. So in this case, the vertical line, so notice these functions are the same. So I've already done the work here. So to set the denominator equal to 0, we get x equals 5 as a vertical asymptote and x equals -3. And that's just a no-go zone. Vertical asymptote, you can't have the function exist there because you're dividing by 0. So here, the vertical line, x equals 5/3 is a vertical asymptote. Here, there are no vertical asymptotes. And here we have t equals -1, t equals 7, and t equals -3 are all vertical asymptotes. Now, to find the horizontal asymptotes, you're going to look at the degree. If the degrees match, then you just take the leading coefficients. Like here, they both have degree 1, the polynomials do in the numerator and the denominator. So y equals 3/4 is a horizontal line, that's a horizontal asymptote. Here the degrees match because here degree 1, and so you're going to take the leading coefficients, square root of 2 and -1. So t equals square root of 2 divided by -1, or t equals square root of 2 is a vertical asymptote. Here the degrees match because you're taking t cubed as the highest term here and here. So t equals, the leading coefficient for both of these is going to be 1. So it's 1 divided by 1, or just 1. So t equals 1 is a horizontal asymptote. And here the degrees match. Leading coefficient 2, leading coefficient 1. So x equals 2/1, or x equals 2 is the vertical or horizontal. I shouldn't say, I made a mistake there. We're talking about horizontal lines, not vertical. So I should have said y, sorry about that. And this should be s. S and s, s. We're talking about horizontal lines, not vertical lines. Horizontal asymptotes. Okay, so I did the ones where the degrees were the same. Now I'm going to look where the degree of the denominator is bigger. So that would be here, the degree is 1 versus 0. Here, the degree is 1 versus 0. So these two have y equals 0 as your horizontal asymptotes. And now here, the degree is greater than the denominator. And same here, numerator greater than the denominator. So this would be none. No horizontal asymptotes. Okay, so again, look at that chart that I talked about in the previous video and to guide how you find it. And you're taking, to find the horizontal lines, you're taking the dependent variable. So in this case, y, or here it's s. You're taking the dependent variable equal to the leading coefficients or 0, whatever your situation is.